spaces, and a category had objects, arrows. Every arrow had a domain or source and a codomain or a target, and arrows could be composed. Composition was iterative. Every object had an identity arrow, because both left and right identity for composition. Then we gave some examples of categories. So we had the category of sets, whose objects were sets, arrows were maps, composite was identity. And we had the category of groups, whose objects were groups and arrows were group homomorphisms. We had the category of real vector spaces, whose objects were vector space over R and arrows were linear maps. And we had the category of commutative rings, whose objects were commutative rings and whose arrows were ring homomorphisms. And remember that a ring has to have 0 and 1. Of course, 0 can be equal to 1. That's the 0 ring. And a ring homomorphism has to take 1 to 1. Then we introduced some abstract ideas such as initial object in a category. And that has a unique arrow to any other object. A final object in a category. And then we looked at how do initial objects and final objects look in these various categories that we talked about. Then we also introduced binary product in a category. Given any two objects, there's a new object and it has two arrows, which has a universal property. This triple has a universal property. And such a triple is unique up to unique isomorphism. What is an isomorphism? It's an arrow which is invertible. There's an arrow in the reverse direction such that both composites are the identity arrow. Then we introduce binary coproduct with the dual notion, all arrows reversed. Given any two objects, there's a new object called a coproduct together with one arrow from X into it, another arrow of Y into it, which again has a universal property. If you look at this universal property and you reverse all arrows, that will exactly look like the universal property of product. Product and coproduct are duals of each other under changing directions of arrows. Then we extended the idea of product to a family of objects and coproduct too. So here is a table of products and coproducts in our 4 examples of categories. And then we talked of in product or coproduct for a family of objects indexed by an arbitrary indexing set, need not even be finite. And when that indexing set is natural numbers, and we are in the category of vector spaces, each vector space is R, the product is this set of all infinite such sequences with projection on the ith factor being those projection maps. And coproduct are all those infinite sequences which beyond some finite stage are 0, arbitrary. After some arbitrary finite stage, that sequence should be 0, 0, 0, 0, only finitely many non-zero entries. And the map of each sends that X into that X in the ith place and 0 elsewhere. Those are the maps from here. For commutative rings, we talked about products and coproducts. That was a tensor product. This is where we ended. Now, in hindsight, any questions about yesterday's lecture? Don't hesitate to ask, because your question will also benefit some others who might not have asked it. Answer may benefit them. Okay, since you have kept silent, I need some evidence that this is not because the connection has been lost. So I'll ask some simple question. So should we continue now with new material?
Yes, sir.
Yes.
Okay, good.
Yes, sir.
Very good. So today we are going to introduce metric spaces. And so these metric spaces are objects of 3 different categories that we will consider. All of them have metric spaces, all possible metric spaces as their objects. Of course, you can make many more categories. But I'm going to consider 3 different categories. Their objects are all metric spaces. Therefore, now all of you know the definition of a metric space. Am I right? Yes?
Yes, sir.
Yes, sir.
Yes.
Yes.
So what is the definition
Yes.
of metric space? Any one of you quickly say, very rapidly.
Take take a non-empty set X,
Okay,
then
stop
it
right
is
there.
a
Stop right there. So it looks like I have to give the definition. Okay. So I am going to give the definition of a metric space. Definition. A metric space is an ordered pair XD, where, of course, this is what you meant, I am not disagreeing with that, where X is any set can be empty. Okay, and D is a map from X cross X into R such that 1, 2, 3. What are those things? Whatever they are, you know those conditions. What are they? dxy greater than equal to 0 and dxy equal to 0 is equivalent to x equal to y, and dxy equal to dyx and dxy plus dyz equal to dxz. Okay, so you see already I departed from your textbooks by allowing the metric space set to be empty. As I told you, they were very afraid of empty sets in all those foreign countries. Indians were never afraid of empty set, Buddha onwards or even earlier. And so for no reason at all, people will say non-empty, non-empty, non-empty. Okay, but then that made certain things impossible for them. After all, you need 0 in order to count and to have the decimal expansion. 105, 1 second power of 10, 0 first powers of 10, and 5 zeroth powers of 10. You need the concept of 0 even to write things in decimal expansion, which, as you know, came from India, because Indians were comfortable with, don't take any tens. The set of tens is empty. The set of hundreds is singleton. The set of units has 4 or 5. That is 105. Those many Kauravas were there. Okay, or whatever. Kauravas plus Pandavas, whatever. Okay, all right. So, you see, now anybody wants to tell me, in all your experience, where did you use that a metric space is non-empty? You all learned the definition that it's a non-empty set. So I'm asking, where did you use it's non-empty? Have I lost the connection? Okay.
No, sir.
No, I have not lost the connection. But have you used non-empty anywhere?
Yeah,
So if you use non-empty anywhere, henceforth you will have to say that let X be a non-empty metric space, then blah, blah, blah. I'm going to give you an example of such a theorem. It's called Bayer theorem. Bayer's theorem. If X is a complete non-empty metric space, then X is not the union of any countable family y0, y1, y2, blah, 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 of nowhere dense subsets.
Can you hear me, sir?
Yeah?
Yeah, I cannot read. The last thing I can see on my screen is not the union of any countable. I'm not sure if
Countable family y0, y1, y2, blah, 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 of nowhere dense subsets. Okay.
No, I understand that you wrote that, but I can't see that on the screen. So I was just wondering if it's a problem at my end or if others have that.
Sir,
Hmm.
there
Yeah,
is delay. What you write
there's a
come
delay
after few times. There is a delay in these
because the
ones.
connection may be slow, you see.
Yes, sir.
So slowly the letters will appear, but perhaps the voice has much less data, it comes fast. You know, the speed of sound is greater than the speed of light in this. Okay, so but you have heard me, so is there any doubt on this one? This is Bayes' theorem, right? So people who insist that metric space has to be non-empty will be saved from writing non-empty in this theorem because they would have already assumed non-empty. Is that some great advantage? Not exactly. It's a good reminder to say that, oh, suppose it's a complete non-empty metric space, then you'll check whether your space is non-empty also. Sometimes people miss out on whether the space is empty or non-empty, and then they think they have something, but actually there's nothing. So there may be a few such examples like Bayes' theorem in which you may have to explicitly state that your metric space is non-empty. Otherwise, there is not going to be any problem. And you will have much more things available to you. You can take intersection of two subspaces of a metric space, and that is again a metric space. Yeah. In the earlier definition, is the intersection of two subspaces of a metric space with the induced metric, again a metric subspace. Then you'll say, oh, provided the intersection is non-empty, it is. You see, you'll have to then go on saying provided non-empty, and then what happens if it is empty? You'll have to go on making cases. Is the intersection of two compact subsets compact? Yes, empty set is compact. You know, empty set is compact, empty set is connected. It has all these nice properties. An empty set is complete. How many metrics does the empty set have?
Just one,
Yeah.
right?
Many of.
Infinitely.
How many metrics does the empty set have? Suppose I want to define the empty metric space. My underlying set is empty set. What metric can I define?
So there's one metric.
There's exactly one metric. Yeah.
There's just one metric.
You know, a metric is a map like this, right? Satisfying those three properties for all x, y, z. So if X is empty set, then what is empty cross empty?
Empty.
Empty.
You have just
How many
the empty
maps
map.
are there from empty set into any other set? Exactly one. Because empty set is initial set. Yeah? Empty is initial object in the category of sets. So this is my map. There's only one map, and that is D. Now, does it satisfy these three properties? Of course. It says for all x, y, z. So give me some x, y, z, and I'll show you it's satisfied. So as they say, 1, 2, 3 will be vacuously satisfied. 1, 2, 3 are vacuously satisfied. It's like saying that every time I climbed Mount Everest, I had Bhelpuri at the top. Absolutely true statement. Tell me any instance where I climbed Everest but failed to eat bhel puri at the top. You have been there. So you see. Okay. So there is the empty metric space. And I'll simply denote it by its underlying set. You see, you are used to the notation business, which we also use in groups. I'll suppress the notation D if it is understood what is D and simply denote the metric space by the same letter as that of the first part of this ordered pair. Okay. So at this point, any questions? I introduced what are metric spaces. Okay. And I also told you I'll allow them to be empty. I also told you where you may have to take care because I don't automatically assume them to be non-empty because in certain theorems, now you'll have to write non-empty in the statement. And what advantage will I have by also allowing empty? Because then I have an initial metric space, I have intersections, and empty set is not so fearsome. It will keep coming up all the time. And you don't have to then all the time say if non-empty, if non-empty. Okay. All right. So now I'm going to make it into category. So I have two metric spaces, X, D, and another one, X prime, D prime. And I want to define an arrow. Question. How should I define an arrow? F. Here's F. So let's take some inspiration from our group theory. In group theory, you had G, and this is a group. And there was another one, G prime, and let's show this is its operation, and I want to have some phi. And then what did you demand? Phi of G star, phi of H equal to phi of G dot H. Yeah. So phi preserves, phi takes multiplication to multiplication. So with this inspiration, you know, you will be excused. It will be perfectly justified if you say that. So that will be definition one. F x d to x prime d prime, an arrow, is a set map f from x to y, sorry, x to x prime, such that this distance between 2 points x and y of x is equal to the new distance between their images. So such that I don't keep writing for all blah blah blah. What I say such that for all x, y belongs to x. So this is one definition. This definition has a name. We say that f is distance preserving. Okay, so let's go back here. I said we'll make three categories whose objects are Paul Russell metric spaces. The first category are metric spaces with distance preserving arrows, distance preserving maps. So this is going to form a category. Okay, so this gives a category. Metric spaces with distance preserving arrows. Distance preserving. So before I jump to the conclusion, it's a category, I have to check certain things. How about composite? If this is distance preserving and this is distance preserving, then GOF. So will that be okay? Somebody reply. If both the first and second map are distance preserving maps between three metric spaces, is the composite distance preserving?
Yeah. It's because of
Yes,
compositions of isometry will again be isometry.
Yeah, that's what I'm asking. Is composite of isometry and isometry? Oh, you are saying distance preserving composed because isometry is composed. That appears to me as just a playing with words, no?
Yeah, but yeah. So by our definition, we can in fact
Exactly. You just apply the definition. Yeah. So therefore, but good you brought up that word isometry. Distance preserving is also called isometry by many people. I have a slight problem with that word because some people call isometry a bijective distance preserving map. Some others call isometry, by the isometry they mean distance preserving map. Some others mean preserve that word only for bijective distance preserving map. A distance preserving map is injective, yeah, automatically. Exercise. If F is distance preserving, then F is injective. Give an example where F, such an F, not surjective. So all of you must have in your mind thought of a distance preserving map which is not surjective. Trivially true. How about when F is from X to X itself? More difficult exercise is give an example of a distance preserving map F from XD to itself such that X, not X, such that F is not surjective. Okay, so let's look at this first point. If F is distance preserving, F is injective. Why? Yeah, because if it's a distance preserving, yeah, all of you understood why it is injective. Because if two points are brought together, then the distance has become zero. Earlier, the distance was positive because of the first condition of metric space was if 2 points are not equal, then the distance is strictly greater than zero. Distance zero means the point have to be the same. So if 2 points are not the same, then the distance is positive, and if distance is preserved, then the images also cannot be the same. Therefore, it is injective, but need not be surjective. After all, a point sits in any large metric space, and that map of inclusion of a point in a large metric space is distance preserving, but it's not surjective. So more interesting is when such a distance preserving map is from a metric space to itself, and it need not be surjective. Have you thought of an example already?
Probably shifting any point by some one
right
On
shift
what? What's
operator
your
on
space?
L2.
What's your space?
n. Take the natural numbers and consider n going to n plus 1.
Okay, all right. So that is fine. Yeah, good. You can take a real half line, the positive real axis, and shift it to the right, for example. That's distance preserving, but not surjective. Or you can take a discrete metric as you took in your example. I suppose your metric was discrete. I don't mind what it was. Anyway, it's a translation invariant metric. Okay, so all of you have understood this category. It has composites. Is there identity? Yes, of course, identity map does preserve distance. Then what else do you need in a category? Composition is associative, obviously associative. Yeah, so we have got a category of metric spaces with distance preserving maps. Now I'm going to introduce a second category. Second category has a second number. The second category is non-expanding, met non-expanding. Objects are metric spaces. Arrows from xd to x prime d prime. An arrow has to satisfy, let's call it f, it should not expand, which means the distance between x and the new distance between these has to be less than or equal to the distance between x and y for all x, y belonging to x. So now again, this gives a category. This gives a category. You see, I called it non-expanding. Some people use the word contracting, but some others use the word contracting when there is the distance strictly decreases. Here, distance is allowed to be the same. So metric spaces with non-expanding, you understood this category? Is it clear what's this category? Is this category different from the earlier category of distance preserving maps?
Yes, sir.
Yeah, why? Objects are the same.
Because over here, yeah, that's okay, but morphisms aren't the same.
Morphisms
over here,
are
you
not
have a
the same.
morphism which sends everything. Yeah.
Yeah, what's an example to show morphisms are not the same?
For a non-empty metric space, send everything to 0, to 1 point, sorry. Take a constant map. That is not distance increasing, but it certainly is not distance preserving.
You only said non-empty. You should have said something like it should have more than 2 points.
Yeah, sorry, yes, of
Two
course
or
I mean more than 2
yeah.
points. Yes, you're
So
right.
if your metric space has 2 or more points, a constant map, you after all have the constant metric space, singleton point, and the distance between that and itself is of course 0. And then there is an arrow from here to there, yeah? So you see, already we have, your example was very nice. You talked about a constant map, and therefore that inspires me to make the next statement in a very motivated manner. Met non-expanding has a final object.
Yes, that's.
And what's the final object? A singleton metric space.
Sir, I wanted to ask you something.
Yes.
When you said that you allow metric spaces to be empty,
Right.
that allows you to have an initial object.
Yes,
so I was thinking, are there, so that are there categorical benefits of having something
great.
like all?
Great categorical benefits. Yes.
Okay.
And you will see them all the time. Yeah.
Yeah,
When you say that, oh, given any other, there's a unique arrow from here to there that is making this one an initial object in an appropriate category.
Yeah, colimits will exist, and so I can talk about colimit topologies.
All such things are initial objects. You see, colimits and limits are terminal objects. Yeah. Yeah. Initial objects, terminal objects is the model for all kinds of other constructions like limits, co-limits, products, co-products, all your standard things. Tensor products, direct, everything, all these universal properties are finally boiled down to initial or terminal objects in an appropriate set.
Yes.
So initial terminal objects very important. Okay. So this has a final object. but this had an initial object. Okay, we'll make a table later. But met, what was it called, DP, has an initial object but no final object. So you will have to prove that it has no final object. Yeah. How will you prove that it has no final object? So this is exercise. This is going to be exercise. Exercise. So Saibal, you are there and you are noting down the exercises, yeah? Saibal, do I hear from you?
Sir,
Okay.
actually, my internet connection went off, so I missed quite a bit. So if you can send me this slides, I can.
All the time, every time I send you the file. After
Okay.
every lecture, you get a PDF file of the whole black.
Yeah. That's enough for me. I'll
That's
find out a bit.
good. You can reconstruct the rest easily. So here's an exercise actually that shows that. So later I'll say more things. You see, these are actually subcategories. Metric, DP.
Sir?
Yeah, bolo.
Sir, in this Matt Annie, can you explain how a singleton metric space is a final object?
Yes, I will. Okay. So here's any metric space. D. And I am saying there's a map from here to there. This is a singleton. Of course, there's useless trying to write a metric on it because the distance between it and itself is 0, right? So there's no point wasting notation on the metric. So I'll only write the set. Okay. So I have this map f of x equal to this. Now, is this non-expanding? So f of x and f of y. What's the distance between f of x and f of y in this metric space below?
0, sir.
That's always 0. And what might have been the distance between, so this was distance in x. Distance in x between x and y is greater than or equal to 0. The first rule of metric spaces, that the distance is. Therefore, the distance has become 0. Earlier it was greater than or equal to 0. Therefore, distance has not increased, right?
Yes, sir.
It may have decreased, it may have remained the same. For all you know, x was equal to y and the distance was already 0, then it has remained 0. But if x was not equal to y, then the distance was positive, and positive has become 0, so it has decreased. So either it remains the same or it decreases, which means it is not expanding. Expanding will increase the distance.
Okay, sir.
Okay, good, great.
Sir, and like we have this non-expanding metric morphism. Like, can we have an expanding morphism like the inequality sign is reversed?
You try. I told you, you can make many more spaces. The question is whether they'll be useful.
Sir, like I was actually talking about morphisms.
So all this later, you see.
Okay.
There's great scope for you to play with this, and I'm very glad that you are already playing with it. It's very important in mathematics that you hear some definition and say, hey, what if I change this condition to that? What if I make a little twist here? Or what if I alter this? What if I put one more thing? This is how mathematical research happens. People ask questions. So I like your spirit. You are already doing research on what might be categories whose objects are metric spaces. So do it outside the classroom though. And tell me if you arrive at any interesting results. Finally, whatever definitions you make, there should be interesting theorems. Otherwise, the definitions, it becomes a game by itself. And those theorems should refer to things which don't refer to that definition. In other words,
Okay,
you should be able to answer old questions by means of your new definitions and theorems. Old questions which did not have those words in them. Yeah, that is the test
Yes.
for this. Okay. So with this, go ahead and play. And play is very important. To play is not to take tension that, oh, I have to get something useful out of it. To play is to just have some fun. Spend 15 minutes, waste them. Yeah, it doesn't matter. That's how you develop your mathematical muscles. So very good. You play with these definitions, make various tweaks. I can suggest to you variations on this, but it doesn't matter. Okay, so let's come to this point that it is a category and it has both initial and final object. And also I pointed out that every distance preserving map is of course non-expanding. So this is a subcategory of that. Every arrow in this is already an arrow there. Composite here is composite there. Yeah. But this thing didn't have an initial object, and this thing did not have terminal object, and this thing has. And the initial object remains the same after going from here to there. Okay. Now we come to the third one. The third category deserves the third color, I suppose. It's very funny how many colors this damn thing has. Okay, therefore I have to use. So the third category is met continuous. Okay. So here F from one metric space xd to x prime d prime, you have already guessed the answer, is a continuous map. Okay. All of you know the definition of continuous map, yeah?
Yes.
Yes. Is there anybody who wants to hear the definition of continuous map? No, you know it for the last few years, I think. Okay. So now again, this is a category. So again, what you have to check? Composite, associativity, identity, arrow. I think that's about it. Yeah. So in this category, what do you have? Initial object, it's still the empty metric space. Terminal object, the singleton metric space. So tell me, are non-expanding maps continuous?
Yes, they are.
Yeah.
Yes.
Yeah.
So
Yes.
every non-expanding map is continuous. To our friend who wanted to play with expanding maps, would they turn out to be continuous?
Yes, sir.
No.
Yeah, non-expanding maps will be continuous.
No.
but
You
Expanding.
wanted to reverse the definition and say that, oh, I'll allow the distance to increase.
No, sir.
Non-contracting
Then I
you
don't.
wanted. Instead of non-expanding, you wanted non-contracting. So non-contracting maps won't be continuous, yeah?
Yes, sir.
Not necessarily continuous. So you see how much you lose out. Okay.
Yes.
Yeah. But very good. And you have to ask these questions. Only then you digest a definition, because every little word is meaningful. But you understand that meaning only when you try to change it. And then you see what goes wrong. After all, we changed the definition of metric space right at the start of this lecture, we said, why do you want it non-empty? Let's allow empty. And let's be careful in some other places where you need non-empty, we'll put it in explicitly there. So yeah, you have to play with these things. Okay, so this means that met distance preserving is a subcategory of metric non-expanding and is a subcategory of metric continuous. You know, these are subcategories because the objects are not increasing. Objects have remained the same, but the arrows have increased. You can have subcategories in which the objects also are more, you see. After all, you can have, for example, you can take the category of finite dimensional vector spaces and linear maps for real numbers. And you can take the category of all vector spaces and linear maps for real numbers. Then finite dimensional vector spaces is a subcategory of all vector spaces, but now there are more objects. Between the old objects, the arrows have remained the same. There are no more extra arrows between old objects, but there are more new objects. That kind of subcategory is called a full subcategory. In this kind of subcategory, the objects have not increased, but between the same old objects, there are now more and more arrows. There are many more non-expanding maps, and there are even more continuous maps. So let us establish this once and for all with an example. So example. Okay, first of all, let me say that an isomorphism in metric non-expanding is just an isomorphism in metric distance preserving. Why? So here, should I call it exercise? Saibal, are you able to hear me? I have again lost it. Makran, are you able to join?
Yeah.
Yeah,
Actually, I'm muting myself, so that is the reason.
You don't respond rapidly. Okay, no problem. So you have noted this is an exercise, and I am asking the students to show that an isomorphism, a non-expanding isomorphism, is just a distance preserving isomorphism. Is that obvious?
Yeah.
Because you see, if it had already contracted some distance, then the inverse will have to expand that distance so that, you know, the composite is identity. But the inverse is not allowed to expand. So you go from x to x prime and come back from x prime to x and everything remains as it is, means you have never done any actual contraction. You all the time kept the distance as it is. Is this statement obvious now?
Yes, sir.
Yes, very good.
Yes, sir.
So isomorphisms, there are no new isomorphisms in MET any. Isomorphisms are already there in MET DP. But I'll give you an example. 0, 1 with dxy equal to mod x minus y. And R with same. Are isomorphic in MET C, but not isomorphic in MET non-expanding or MET distance preserving. Distance preserving isomorphism is non-expanding isomorphism. Yeah. Clearly, what is the size of this? This has length 1 and this has infinite length. If distances are preserved Here you cannot have any 2 points such that the distance between them is 5, but here you have lots of points such that distance between a pair of them is 5. There are lots of such pairs. So they cannot be isometric. Yeah. If there's a non-expanding isomorphism, it's a distance preserving isomorphism. But these are isomorphic in met C, which means there's a continuous map. There's a continuous map from R to 0, 1, F, continuous. And there's a continuous map G from there into R, again continuous. So that GOF is the identity on R and FOG is identity on 0, 1. Can you give these maps? Can you give such maps?
Yes, by
Sir, variation of NX maybe.
You can give concrete formulas for this in many ways. You can use trigonometry, blah, 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 tan function. Tan.
Yes, sir.
Yeah, but
T by T square minus 1.
You can try many formulas. There's no unique one. After all, I has plenty of automorphisms. Therefore, such isomorphisms are not unique. You can always compose it with some automorphism. Yeah. Okay. So you understand these 3 categories of metric spaces. Now I am going to ask you something very remarkable. Okay. So now I want to know, I want to have products. Direct product or binary product. Direct product, binary product, whatever. X cross Y. X and Y metric spaces. I will now stop writing my metric space as X comma D, Y comma D prime. I'll simply write it X, Y. So I want direct product of metric spaces. Yeah. Now let me ask you, you have been to school, college, whatever, college onwards. College onwards, you have been taught metric spaces. Am I right? In BSc, were there metric spaces? In your
Yes,
BSc.
yes, yes,
And in MSc, again, you have studied metric spaces?
yes,
Yes. Have you seen direct product of metric spaces?
yes.
Okay. So how is it defined?
Uh, uh, if D1 is a metric on X and D2 is a metric on Y, then we define D as the maximum of D1 and D2.
So this is one possible choice. Somebody has given me one possible choice. Yeah. Under which distance between X, Y and X prime, Y prime equal to, this is one possible choice. And what was your choice? What did you say?
The maximum of
Max of
D
X prime and D
Y.
Y. This was one possible product. Okay. Has somebody seen any other formula?
We can add them.
by taking.
Yes, somebody said add.
Yeah, add those dx, yeah, plus dyy dash.
Has anybody seen anything else?
Yes, sir.
Tell me.
So it's the norm in R2 of it's a 2 norm in R2 of dx of the point which has coordinates dx comma x prime and dy.
Has somebody
comma y
seen
prime.
any other formula? Have I written your formula correctly?
Yes,
Is my board?
yes. This one,
Has
the
anybody
norm.
seen anything else?
Take the modulus and then
You can take
yeah, I mean all of them will be equivalent in
because in R
but
so you
I
can
mean,
take any of the
a lot of
You have all kinds of possible formulas, right?
yeah.
But you know that a product is unique up to unique isomorphism, yeah?
Yes.
Yes. So isomorphism in what category? So
top.
they have, these different choices have to be isomorphic in your category, right? They are clearly not isomorphic in distance preserving category, right? Clearly not. They are
Yes,
giving
yes.
different answers. Yeah. So,
Yes.
so this has no, so met DP does not have products. Have X cross Y, Px, Py in general. Okay. So exercise. Of course, sometimes it does have. If X and Y are empty, then yeah, the product is empty. Or if X and Y are singleton, product is singleton. Or if X is singleton and Y is anything, then X cross Y is Y, and so on. But suppose, so here's the exercise. Suppose cardinality of X is greater than or equal to 2 and cardinality of Y is greater than or equal to 2, then X cross Y, Px, Py does not exist in met DP. You see, met DP is a really handicapped category. You know, we began by making it sound very reasonable that, well, we have rings and then you define a homomorphism so that it preserves addition, multiplication, 0, 1, etc. So you may think you have metric spaces and now you have a map which preserves the metric. Very reasonable definition, but that reasonable definition does not produce something which has many nice properties. This may sound strange to you, but slowly I'll help you understand this by making more and more comments. Yeah. So the metric DP is not a very nice category for our purpose. For some purposes, it is important. You try telling a taxiwala that, you know, metric DP bad category. He'll say, no, no, I want to be paid for what distance I take you. Okay. So don't tell me that this is equivalent to something else under a continuous map. I take you 500 miles and under a homeomorphism, the journey has become only 5 miles. Therefore, you'll pay me for 5 miles. Ye nahi chalega. Okay. So it depends on for what you want to use metric spaces. If you want to use metric spaces where the size is really important and you are going to make important arguments based on size and its inequalities and whatnot, this is the case in analysis. This is the case in functional analysis. So when you are doing analysis or functional analysis, it is very, very important that you pay attention to the actual value of the metric. And then you will want distance preserving things. But at the other extreme, if you are doing topology, then you don't care for the distance. And you expand, you contract, everything is okay. And then you take met C. And this met non-expanding is somewhere in between, which allows you to do many things, many more things than the distance preserving one, but is a bit more restrictive than the topological one. Yeah, and you will see what is what. So after the first week or after maybe 2 or 3 lectures on, at the most 3 lectures on metric spaces, I want to go to topological spaces anyway. So, but at this point, yeah, there are so many things I want to tell you, and we are again, as usual, running out of time. All right. So let me see what I have finished telling you today. I have told you that we have the category of metric spaces in 3 different ways, and you can have many more. Objects are always metric spaces, and the arrows are distance preserving maps, or non-expanding maps, or continuous maps. And then I also told you that for metric spaces, I'll allow the underlying set to be empty. Then I told you that because your various books automatically assume non-empty, in the statements of some theorems, they don't mention that because they already assume non-empty. So in certain theorems like Bayes' theorem, you'll have to mention non-empty. Have you guys seen Bayes' theorem, any of you, anytime?
Uh,
Sometimes
Yes,
called.
sir.
Under
Yes.
category theorem, but that word
Right.
category has nothing to do with category in our sense. Huh? Yeah. Okay. So this is a very important theorem and it requires non-emptiness. Otherwise, it's not true. You see, the empty set is the union of the empty family of empty sets, which are nowhere dense. Okay. So you will have to simply add non-empty to the some other statements. Then I introduced to you the three different kinds of morphisms. And then we talked about whether they admit initial object, final object. And now I am talking about whether they admit product. So I have told you here with an exercise that the distance preserving one does not admit product. Okay. Now look at all these candidates for products. I want you to tell me whether they are indeed product. Does the resulting triple, for example, is the projection non-expanding? And you'll see that all the projections are going to be non-expanding because you are taking max of dx, x prime, dy prime, or sum, or whatever. If 2 points go to the same point, then here the distance is going to turn out to be the same as before. So this is not, yeah. So they are non-expanding. They can actually contract. They may contract, they may not contract, but they definitely do not expand. So all these are candidates for a product in MET NE. So let me write here the answer. All these are okay in MET non-expanding, where the triples, the resulting triples, x cross y, px, py are uniquely isomorphic. Isomorphic to each other. And the map, the isomorphism, is identity on the set. Yeah. So you check this, which of these is okay. Can't all be true. So here I am asking you a question. This I should question. Are all these okay? Are all these okay? Let me make it. Clearly, the distances are not the same, so may involve expansion in one direction and contraction in another. And otherwise, which one? If not all these, then which one? One of them is going to work at least. So tell me which one is going to work. And that's going to be your product. And the other metrics are equivalent to that metric. So here I'll say all these work in MET C, where x cross y, px, py resulting are isomorphic to each other, and the isomorphism is identity on x cross y on the set x cross y. Yeah, this much one of you already said. You said all these metrics are equivalent. One of you said it. Yeah, remember? And that means the topology is the same, which means in this category they are all equivalent. In the non-expanding category, they are not all equivalent. I don't think they are all equivalent. Yeah? So you find out which one is.
They are not.
They are not. After all, they are not going to give you the same distance. One is giving more distance, one is giving less distance. Therefore, the identity map is allowed in one direction, but not allowed in the opposite direction. Yeah?
Yes, sir.
Otherwise, it will expand. In the opposite direction, it will expand. If in one direction it's contracting, the opposite direction, it will expand. Or to ask for a simple test. So here's a simple test. Let's see. I will, after all, have the diagonal map of x into x cross x, right? Because there is x. I take both x and y to be x. And this I take to be identity. I am telling you something, one of the most important constructions in mathematics. If there's a direct product, px and px, well, so I'll have to call it as p1 and p2 to distinguish the two factors. Then there exists a unique such map here. And that map sends x to, tell me where it sends, x comma x. This map is called diagonal map of x. And you see how it looks. This is x, and I'm going to draw the diagonal in a different color. This is the diagonal. So now if I take a point x, that means this point x. And if I take another point y, and here is that point y, then this distance, this projects here. This projects here. So x is mapping to this. X is mapping to this blue thing. And in x, there were 2 points, x and y. That distance has to be the same. If you give the Euclidean metric, this distance has increased. It has become √2 times the earlier distance. Clear? If I give the addition metric, it has become twice. Go this way plus go this way. So it seems to me that the only one which is working is this max wala. This is the correct one. So that's why I have written question marks on all this. And are these okay is the question. So this seems to me okay. The other seems to give wrong answers. But in topological category, they are all equivalent and they are all okay. So I run out of time. I am 3 minutes over time. I am stopping.